Share. We were working on the last section of chapter 1.4. The only thing we stopped on the scatter plot. Now we had talked about scatter plots, and the closer the dots are, the more we can find a better equation for them. But we hadn't done an example. So for an example, we're going to use Desmos. I think it's the most user-friendly. You can use Excel, but depending on the version, then you have to download more things. So I think that Desmos is the most user-friendly for it. So you go to desmos.com and click on Graphing Calculator. Now this data is the population and the total number of COVID cases. And that was as of September 28th, 2021. And so I took so many of the countries and took the population and the COVID cases. So if we put these into here, remember to do a table, you click on the plus sign and go to table. So plus sign and then table. And then we type them in. 331, 213, 146, 84, and 84, and 51. Both of these, notice it says, are in millions. 43.2, 21.4. Now, if you open my Word document, you probably could copy and paste it. This was just from a picture, so I couldn't do that. Any questions on that part? Now to find the points, notice that these numbers are pretty high, so they're not on this scale. So what you do is you use the wrench that's over here, and you want to take your smallest and your largest. Now I always go a little bit smaller. I like to use a -1 for my lowest. But then my highest X value, if you look at the X's, it goes up to 331. So maybe I'll go 335. And you can see the points there. Now the Y, again, I'd probably go -1. And the highest value was 43.2. So maybe I'll go 45. But I like the -1 and the +1 because there's my axis. But if the numbers are way too high and you have to use a different value, that's fine. Just make sure you're including your lowest. Any questions on that? So there's my points. One of them's not there. 331. No, why? What was here? Okay, it was just blocked over here. Any questions on the graph? No, if you
How would
So
you
why
copy
do
and
you
paste that?
use a higher number?
say
Like,
that
why
ag-
do you fill up higher?
oh, it was 331. So it was way over here and it was 43. This one was only, if you look at the values, the next one was only 21.
Oh, okay.
How would
Thank
we
you.
copy and paste that in a Word document?
Um, I think the outlines are down here.
You're gonna write something within it that looks like.
So I just copy. Oops. And you Control C.
Does the line above it.
Decimus. And then I'm going to do a separate one. And then right here, Control V. Oh, it didn't do it. I wonder why it didn't. I know Excel does it very easily. I thought this one would do it also. From Excel, puts them in real easily. Maybe if I copy it from here, whoops. Control C. There, it worked that way. So you have to put it into an Excel file first, and then it will copy it.
Okay.
Notice it's the same one because it put them right on top of it. Notice it changed my numbers, X sub 3, X sub 2. You have to be careful of that for the next part. So if you do want to copy and paste it, you do have to put it in an Excel first and then copy it and paste it. I guess I could show you that one too. All right, now to find the line, because remember, we talked about the scatter plot, and then the tighter the line is, the more you can use it as an estimate. And the R squared, the closer it is to 1 or -1, the stronger the relationship. Well, we can find that on Desmos. So if we go back to Desmos, you click the one below it. Remember, a straight line is y equals mx plus b, but this is y1. So we click y, and then when you click the 1, it automatically goes down. Equals mx1 plus b. Okay, why is it not? Oh, that's right. You can't use the equal sign. Instead of the equal sign, next to your 1 on your keyboard, if you hit shift, there's a little squiggly line. because it's called a trend line, and it may not be exactly the value with the data, you use this little line. You have to hit shift and the key to the left of your number 1. It gives you the equation and it gives you your R. Notice R is 0.96. So that means that these points are close to the line and it would be a good estimate. So if we wanted to find someone with 2 million people in their country, we can find out approximately how many COVID cases there were. Any questions on that? So this is giving us an equation. So if we look M right here, I'm going to use 14, so 0.14x minus 6.16. And R is 0.96. So that's close to 1. This is a strong relationship. Any questions on that? Now notice China and India. They have a very large population because this is in millions. So it's 1,439 million. And their cases are really low. If we plug them into this equation that's supposed to be accurate, y equals, we'll do China. What do we get?
An almost positive 1.
Should get a very positive number.
A very positive 1.
Very large. Notice that we're getting 195.3 and it was in millions. So for their population, they should have 195.3 million. And notice they don't even have a million. This, if you times it by a million, 1, 2, 3. At this time, supposedly, they only had 96,000 cases. So either they were lying or it was just, I don't want to call it luck, but maybe they started taking care of drastic measures sooner than everybody else. So these are not always accurate, but it says for most part, there's a strong relationship. But you always have, these would be called outliers. Now, if we put these two, what happened was the first time I did this, I had them in there to see what would happen, and then I pulled them out. If we put those in, we go back here and add them. So 1439 and 1380. Notice how it changed our R. Now it's a very weak relationship. It's almost 0. Notice our line, how it changed. So sometimes when that happens and you have ones that are outliers, let me change my unit so you can see it, because we were only, if you look at the wrench, we were only going up to 300 and some. So 14 I'm gonna go 1450. And X should still be fine. So the outlier here. $13.80. Oh, it's down here. Okay. Why is it 0? Oh, because it's so low. I don't know. What's this one? Oh, 0.096. Yeah, that's almost 0. So these two are outliers. And sometimes when that happens, I mean, technically, yeah, you should include them. But if you want to show a strong relationship and get a good equation that maybe it works 96% of the time, then you drop out your outliers. Because most of them are gathering here, almost looks like half of a parabola. You would take those outliers out. Any questions on that?
What is an outlier again?
One that's further away from your data. So like our population, this one was way larger and it didn't conform then with our line here.
Okay.
So anything that's out of the norm or that's pulling it further away, these are kind of gathered together. These two are out by themselves, so you would omit them. When we omit them, then we have a lot stronger relationship. Any questions on that? So sometimes if there's one a lot further out, then you will omit it. Now in these cases, they're all like spread out. So eliminating one isn't going to help. The same thing here. But if you had one that was way out, say here, then it would change your data, and that's something you would want to drop. Any questions on that? Okay. Chapter 2 is dealing a lot with, it's called stocks and flows, like how much goes in, how much comes out, are the flow. The stock is what the items are. It is a vital insight of ecology and systems theory that in order to understand whether something is sustainable, it's not enough to look at that thing by itself. We have to understand the system in which it's embedded. As the early American naturalist John Muir wrote, whenever we try to pick out anything by itself, we find it's hitched to everything else in the universe. Because I mean, even when I think about, well, I want to organize this corner, well, then that has to go somewhere else, which needs to be organized. Everything links onto everything else. And so it's not necessarily just one thing. And then people get overwhelmed and they're, well, forget it then. If I can't make a difference there, it's just too much. In your book, it talks more about it, chapter 6. In this unit, we'll begin to look at some basic ideas about systems focusing on two things, stock and flow. And so it's kind of going to be what your project is. I didn't think about telling you to say what the stock is, but you can put that in there. Stock is an element of the system that measures the quantity or accumulation of some kind of resource or material that's built up over time. Oh, I guess we did. I told you what the problem was, so that would be the stock. The stocks in a system are what you see if you take a snapshot at the system at some instance in time. So this beach, there was a storm. I don't know if it was, let's see. But notice they have the list of what the stock was. Plastic bottles, cans, paper bags. This isn't a very good picture of my printer. I guess I need to put ink in it. But anyways, all the objects that you can see, that's your stock. It doesn't have to be a physical thing. It can be other things. It could be the air. It's not always something you see. It could also be the amount of information in the library or your own supply of hope in the world. Stock doesn't have to be a specific object. Most of the time, that's what we're looking at it as, but it can be other things.
So it's just like the number of things.
Yeah, anything you can measure. Like we can measure how much information's in the library. Maybe not, hope would be a little, I don't know why they put that in there, but your book used hope, but hoping for better things. I guess it could be a stock. Flow is how much goes in and out. Flow is some process that changes the quantity of the stock over time. So is there more coming in onto the beach? Is there people who are coming in and cleaning it out? And so there's inflow and outflow, which is on the next page. But the flow is the amount coming in or out of the stock. So whatever your stock is, when you're talking about the flow, you're talking about it coming into the area or going out of the area. One that we talk a lot about is the emissions of carbon dioxide. Filling, it could be water in a reservoir. It could be births and deaths. During COVID, it was the first time that there was I think it was 42 states had a decrease in their population, which is the first time since they started recording population. It's the first time there was ever a drop in the population. And so that's things they look at, how they can change that. I think it's just nature finding a way when it comes to births and deaths. Filling or emptying a reservoir. There was one hurricane in Texas, and they had to release the dam because it was going to overflow, and it was better to release the dam and flood a couple hundred homes than it was to have the dam like overflow. It would have been a bigger disaster. And so sometimes they have to take those into concern and see. And so they cleared out that whole area and then they let the dam go and completely demolished all of those homes. But it would have been even more catastrophic if they would have let the dam break. So there are cases like that. You can even think of your bank account, your deposits is the going in, your withdrawals are coming out. And they'll talk a lot about that because I think it's something you use and you think about more than some of the other things. And then it helps you realize the other parts. Emissions, gas emissions from the car, CO2. So all of those are examples that you could look at with stuff going in and out. From that picture, flow could be a storm, and we talked about it, that brought it in, and inflow would be the people who help pick up the trash. That would be your outflow. So a definition for the inflow for a given stock is a flow that tends to increase the quantity of it. So if it's getting larger, then it's an inflow. If it's going down, how much stock there is, then it's an outflow. Now, they're saying it depends on what we're talking about too, because if you think about your account, when you deposit money into it, it's an inflow. When you take money out, it's an outflow. But when you're talking about a company, then it's the opposite. So that's another thing you could look at. When I write a check to the university, it's an outflow from my account, but it's an inflow into their account. So it depends on which one you're talking about. If they give me a check, then it's an out of theirs and into mine. So it could be the same thing depending on which person you're looking at. Any questions on that? Now, diagrams can be used on these. A bathtub is an easy one to think about. Now, the book had another picture. It was nice, but I couldn't copy it. It wouldn't let me, so I found my own. We can represent it in a diagram. And for your project, if you want to create a diagram, you can with the inflow and the outflow and say what's going in and out, how it's happening. Like for a bathtub, you're just turning on the faucet and it goes in. For the outflow, you're pulling the plug and letting it go down the drain. So this would be your faucet. This would be your drain. Any questions? So you can do simple ones. There can be ones that are a little more complicated, which we'll do in a minute. Here's a little bit more. This one was in your book. NASA's Earth Observatory illustrates the carbon cycle for planet Earth. This is a fact system diagram with stocks and flows. Though the graphics are more lively than the spigot and pipes that we had in the last drawing. So this is our carbon cycle. This is carbon. Let's see. The white numbers in the figure are stock levels.
You don't know what it is.
Measured in gigatons, which is 1 billion of tons of carbon. The yellow numbers are natural flow in billions of tons. And the red numbers refer to human caused flow. If we wanted to compute the total inflow of carbon to the atmosphere, these three cases are the inflow. So plant respiration right here is 60. The plant respiration. Air, sea gas right here is 90. And microbial respiration right here is another 60. We add them up, the total inflow is 210. So these are the three that were inflow. If we look at the outflow, there's only two of them, photosynthesis right here. Yeah, photosynthesis, so 90. And right here. So there were two. There was the this coming in, the air sea gas exchange is 90. Oops, so I should put that down. And then the photosynthesis is on land, 120. Notice they're the same. They were both 210. Now, we didn't include the human cause, which is going to take it off of balance. Right now, the amount of carbon dioxide going in and the amount coming out is the same. But if we add in those human caused contributions, then the carbon dioxide will change. It will be different. A stock in a system is at equilibrium if the two are the same, the amount going in and the amount going out. And that was the case here. They were both 210. Now, if you look at your inflow and your outflow, if you subtract them, it gives you your net flow. The net flow, if it's 0, you're at equilibrium, because we had 210 minus 210 equals 0. When those are the same, you're at an equilibrium. Now, that means we add in and remove the same amount, so we kept it equal. If the net flow is negative, then the stock is shrinking. So if the amount in is less than the amount out, then the stock is shrinking. Now, when we're talking about carbon dioxide or trash, that's a good thing because it's getting smaller. But if the net flow is a positive value, then it's getting bigger. Any questions on that? So if you think of your checking account, say you have 100. If you're putting in 20 every week, for let's say savings, so we can keep our numbers small. If you're putting in 20 every week, but you take out 20 because you want to go out to eat and stuff, so you're using your savings account. So if you put in 20 and take out 20, this is going to stay the same, right? Because we're putting in and taking out the same. If we put in 40 each time and take out 20, this is going to grow, right? Because putting this in, we'd have 140. Taking out 20, we'd have 120. It grew. We're okay with that. But if you're talking about trash and it's growing like that, we're not okay with that. Notice this one, the net flow would be positive because we take, this is going in, 40 minus 20 is 20. So it's growing. If we go the other way, and this is less, 10 minus 20 is a negative 10. Your account is going to lose $10 every time. When you're talking about your account, that's not necessarily a good thing. But if you're talking about the trash or the carbon dioxide, and if there's less of it each time, then that's a good thing. So depending on what you're talking about, the negative could be a good thing. If we're talking about the trash we saw on the beach, if there's more going out than coming in, then we're cleaning it up. Any questions on that? When it is the same, your inflow and your outflow, oops, not, this isn't the same. When they're 0, it's a static equilibrium. So, like my kid's savings account from when they were a baby, if I didn't put anything into it and I didn't take anything out, then it would be a static equilibrium. It's never changing and nothing's being added or taken away. So your inflow and your outflow are zero. Dynamic equilibrium is when you do have flow, but the net one is zero. Oops, no, it's not. Dynamic equilibrium is if the total inflow and total outflow are equal, but not zero. Okay, yeah. This is when your net flow is zero. So the amount going in and the amount going out are equal to each other. Neither one of them is zero though. So in this one, coming in and out is zero. Here, your net flow is zero. That's a dynamic equilibrium. It's able to stay equal over time. Now, without humans, that's our atmosphere. But we change that a lot. Any questions on that? The carbon cycle diagram points us toward a discussion and on sustainable issues. Anthropogenic. It means human caused or man-made disaster. Climate change is one of them. The carbon in the atmosphere is almost all stored as carbon dioxide. Carbon dioxide is heat trapping gas, and we know it's bad. So the more carbon dioxide that is brought in, if it's not taken out, then we could have a problem. So we need to try and keep the net flow at zero when it comes to carbon dioxide. Now, these man-made disasters, that's what you're going to have your project based on. Let's look at an example. Example of radon is a radioactive gas that is naturally generated in soils that contains salt uranium. Radon can enter a home by diffusion through the foundation slab. So enter through the foundation slab. Once it's at the home, it can leave by vent or I thought there was two ways. It can leave by vent to the outside air or radioactive decay. So we want to do a stock model. Notice it's coming in one spot through the slabs and it's going out in two spots. So we would have it's coming through the foundation into the house. But then it's going out in two different spots. It's going out the vents or it's turning into radioactive. Now you need to keep this at a low value or a low percent so that it's not harmful. But that's what could happen. So it comes in through the slabs of the house. And then some of it goes out the vents and some of it does not. It stays and becomes radioactive. But that would be a diagram. It doesn't have to be fancy and huge if you have to draw a diagram, just so you can see how it's traveling. So it's coming in at one spot and it's disappearing in two spots. The residence time associated with a stock that is at equilibrium is the level of the stock divided by the flow rate of the stock through the system. The residence time is an average amount of time that a unit in the stock will spend between inflow and outflow.
Back to the town about
If we consider college as a stock flow with a stock of students flowing in through admissions and flowing out through graduation, the equilibrium stock might be 20,000 students. 20,000 sign up each year. And the flow rate could be 4,000 graduating. So if we have a stock 20,000 students and 4,000 graduating. Now, of course, this isn't including students who just quit. Those maybe should be included in our 4,000. But if we wanted to find the residence time, then we take the level of stock, which is 20,000. That's how much is there. And divide by the 4,000 that graduate. And that gives us 5 years. So there's 20,000 students per year. And there's 4,000 that graduate per year. Leaves us with 5 years. So approximately a stock is in college for 5 years. So as that trash is coming in, it's telling you how long it's staying there before it's getting recycled. Any questions on that?
Will the inflow always be on top and the outflow on bottom?
The outflow is on the bottom. This is the total amount. So if we were, it didn't have any values for the trash one, but if we were thinking about it that way, it would be the total trash that is there divided by how much is being cleaned up each year. So this is saying at any one time, there's 20,000 students on campus or going to school. It's not looking at how many, that's not the inflow, I guess. This would be the total students. The bottom could be going in or out, depending on which way you want to think of it. But usually you look at what's going out and it tells you how long it's there. So this is the average. Like if we were going to do the trash one, you'd want to find the average that's there in a whole year, how much it's staying in an average, and then how much is being cleaned up and divide them. Or how much is coming in and divide them. That would tell you how, I think going out is a better example, but this says you can look at it either way, coming in or graduating. If we have 5,000 or 20,000 students on campus at any time, and 5,000 came in. Sorry about that. If 5,000 came in, then they should be there approximately 4 years, because we're trying to keep 20,000 students on campus at any time. If 5,000 came in, then we need them to finish in 4 years so we can keep that 20,000. So it's helping you keep your stock at an equilibrium, or at least at the same amount. Any questions on that? There's only 5 minutes left. Okay. Wanted to show you the project. Under attendance, homework, and projects, there is a new project. When you click this link, it's a Google Docs, and then just put your name next to whichever one you would like to do. Just put your name.
What are these?
These are all disasters, man-made disasters. No. Well, let me go. Yeah, let me go back. The project. Anthropogenic hazards are human-induced or man-made and are entirely predominantly by human activity and choice. Now, sometimes, like if you have, I don't know, maybe oil cans stored somewhere and a storm, they're damaged, but you haven't changed them and a storm comes through, then it's still considered man-made because it wasn't properly disposed of and taken care of. So it still was the human fault, even though a storm might have caused part of it, but most of this is mainly human at fault. And here's some examples. Vegetation removal. If you remove vegetation, you're not getting all the oxygen. If there's a storm that comes through, there doesn't slow down the water, it takes the dirt, things like that. And so I put the link here also, either one is the same, but you need to create a PowerPoint with at least 5 slides, pictures, at least 3 of them. What happened, is it still affecting the environment, like the inflow and outflow? How could it have been prevented? Include and explain a graph. Now, whether you create the graph or you find a graph online and explain it, it's up to you. Include percents and numbers in your explanation, like explain what those numbers are. If there's very large or small numbers, humanize it. They should all have big numbers. Works cited. Once you post it, make sure to respond to 3 other people. I made an example. Maybe it'll open. The Great Pacific Garbage Patch. And this is floating in the water. I think this one's near California. There's 3 or 4 of them, but this is the largest. It's called the Pacific Trash Vortex. Notice I put number, it gave me square kilometers, 20 million square kilometers, but then I also put square miles, and I used some scientific notation so that I'm showing both things. So if you have large numbers, scientific notation. Scientific reports, that was the company, reveals 75 to 86% of the plastic debris in the Great Pacific Garbage Patch originated from fishing. So most of it is from fishing, but other things, like we take all of our plastic and we ship it over to China to be recycled instead of recycling it ourselves, and it falls off the barges. So that is some of it too. And it comes from other countries. And I think this one, maybe I didn't put it, but there's a picture. I thought I had it in here, where it shows you the 2 currents and the way that they spin. That's why it's all landing in one area. Here it gave me value. So I used this graph. It's kind of like a pie chart and telling you how much of each kind is in there. And so I found 80,000 tons of trash, said right here. Well, a saltwater crocodile is about 1.45 tons, which I didn't realize they're that big. So they're the size of an elephant. It would take 55,000 crocodiles in that area to cover the amount of trash. Didn't realize how big. 46% of the total mass is discarded fishing gear. So I took 46%, wrote it as a decimal, and I took my 80,000 tons. And so 46% sounds like a lot, but that's only 36,800 tons of it. And so there's a lot more coming from us than, I mean, you see 46%, you think that's more, most of ours, but it's not. Now this one's had a little different than the last one, but anyways, so that's 25,000 crocodiles out of the 55. So I used a percent and I found some values with it. So you not only want to convert like we did with the humanizing project, you also want to use a percent. Now it's up to you for your table. If you create a table, you could compare it to other disasters that are similar, or you can find one that's given any type of graph. Time graphs are usually, you find a lot of because how it's changed over time. But then you can look at this. I did an inflow. I probably should have put garbage coming in. It's all landing there and out, but I didn't put the percentage, but the inflow is greater than the outflow, and that's why it keeps growing. $1 million seabirds and 100,000 marine mammals are affected every year, as well as many other species. How could we prevent or clean up the Great Patch? This is one where it's kind of hard because it's hard to know how do you start, but you got to start. And so, and then you would put your works cited. Remember to respond to 3 classmates. So something like that, you need at least 5 slides, follow the rubric. And if you have questions, let me know. Any questions?
John, I have a question in the chat.
Oh, I'm sorry. Thank you. On slide 3, did you create that? I did not. That one, I found one online. So I didn't create one, but you can, it's up to you either way. So if you want to create your own, you can. If you want to use one that's given, make sure you cite it in the works cited. Any other questions? It says we need editing. Oh, all right. I'll figure that out when I log off to let you edit it.
Have a good one.
Thank you.
Have a nice day. Bye.